So let us start this. So we completed till over here, like Gauss law of magnetism. Then we understood how to find the magnetic field for the moving different charge kind of systems and all this kind of things. Why not? Now today we are going to look into a basic start of a new topic, which is commonly known by a name called as Lorentz force. Your school has not been started yet, no? When it is going to start? Acha, August August 28th. Okay. Let us write this magnetic force on moving charge. Okay. So August 20, then we can plan for rotational and center of mass class. Word or not? You share me your schedule, then I'll plan myself. Okay. Yeah, that I have definitely. उसके हिसाब से ठीक है करते हैं जरूर ठीक है. तो देखो अपन बात करने वाले हैं टुडे. आई एम गोइंग टू टॉक अबाउट लॉरेंज फोर्स. वर्ड और नॉट. नाउ what is this basically? What is meaning of this? Now till now we studied how to create magnetic field, how magnetic field was generated, and what used to happen, how the charge will move and it will generate a magnetic field, all these kind of concepts. So till now we understood the generation of magnetic field, isn't it? Right now this topic will make you understand how to feel the magnetic field. Yeah. So this topic deals with how to feel the magnetic field. My voice is clear now. So, question arises that if I'm talking about feeling of magnetic field, that can be felt by only some charged particles, isn't it? Yes. Moving charge only moving. We do not know whether it can be at rest also. It can feel. I do not know. Void or not. So we'll talk about that. So it must be felt by some charged particle, which is placed in some kind of external magnetic field. Are you able to get me or not? Let us write charged particle placed in the external magnetic field. Means let's suppose I just throw, like let's suppose I am Anurag, and what happened suddenly I see, let's suppose when I see good food, then I'm like, okay, leave Anurag diet and go for the good food, void or not. So this is what happens with the charge. When it sees the external magnetic field, it starts to experience deviation. And when it experiences deviation, we can say that yes, there is a presence of magnetic field. Are you able to get me or not? So let's imagine, let's suppose there is a charge which was originally going with some velocity v along this direction. Are you able to get me or not? And there was some magnetic field which acted on this particle, making angle theta with the velocity of the particle. Got it? So what happened that when this magnetic field was acted on this positive charge with some velocity, we saw some deviation in the charged particle. Suddenly the charged particle started to feel some kind of force unexpectedly and it started to turn. The point was that why it is turning. Yeah, so basically, yes, so that force which was provided or which was present, force present on the moving particle was given as, or it was told as, Lorentz force. What it was told as? Lorentz force, because this Lorentz was the first scientist who actually talked about this. Are you able to get me or not? Yes. So question arises that when I'm talking about this Lorentz force, what is the magnitude of this? So as the velocity of charged particle is a vector quantity and magnetic field is also a vector quantity. So basically, if this force is feeling some, if this body is feeling some force, it must be feeling along the cross product. So this force was given as Q V cross B, because when they saw the deviation of the charged particle, they saw that they are, as V is along J cap, and let us imagine that this magnetic field along some I cap and K cap. So they felt that this charged particle is deviating inside the plane of the paper. Are you able to get me or not?
Yes.
Because when you use Fleming's left hand rule, which rule?
Left hand.
Fleming's left hand rule, you will see that this velocity and magnetic field, if they are making some angle theta, then the direction of force can be given by Fleming's left hand rule. Are you able to get me or not?
Okay.
Is this clear? Right hand, Fleming's
Yes.
right hand rule is for the generators, but Fleming's left hand can be utilized for talking about the force. Are you able to get me or not?
Acha. So for
Okay.
force we use Fleming's left hand.
Yes. So look over here. This force is very, very important. Remember that here the charge is, if I consider the charges must be taken with respect to sign.
Okay.
Is this clear or not?
Yes.
And this force is only given or called as Lorentz force. Are you able to get me?
Yes. Yes.
So basically, in a normal form, this can be written as F is equal to QVB sine theta, where theta is the angle between velocity and magnetic field. Are you able to get me?
Yes.
Is this clear? Now, question arises that on what properties, or what is the properties of these forces?
Yeah. Got it.
First important point, it depends on the velocity of the charged particle. That means for a static charge, this force is exactly equal to how much? Zero.
Zero.
Yeah.
Yeah.
Are you able to get me?
That is for magnetic
Yes.
force. Yeah.
Second thing is, as this is dependent on V and velocity depends on observer, so this force, remember that this force is observer dependent. Change the observer, force changes. Are you able to get me or not?
Yes.
Because our velocity vector is observer dependent.
Yeah.
Are you able to get me or not?
Yes.
Is this clear? Next point, this
Yeah.
force, as we know that if I take a cross product, then if I write vector C is equal to vector A cross B, then rule is very, very simple, that C vector is always perpendicular to the plane of vector A and B, isn't it?
Which is perpendicular to the cross product.
Yeah, plane, no, perpendicular to the plane of vector A and vector B, not only cross product, plane.
Acha.
Let's suppose there is two vectors which are present in this plane. This radius is given by r vector, okay, and I'm rotating with some force vector. Are you able to get me or not? Which
Yes.
are present in same plane. Okay. So then C vector is always going to be present along this normal. Are you able to get me or not? This is C vector, which is this is vector A and this is vector B. Are you able to get me or not?
So it's showing that it's perpendicular to A only.
So basically C is always perpendicular to the plane of A and B. Got it or not?
Acha.
Is this clear?
Like,
So this
yes,
is
it's
the rule
clear.
of vector. So basically I can define also over here. Third point, that this force is perpendicular to both velocity vector and magnetic field vector. Are you able to get me or not?
Yes.
So that means if you take velocity dot force, that is equal to 0, and if you take force dot magnetic field, that is also equal to how much? 0. Is that clear or not?
Yes.
Got it?
Yeah, that's fine. Okay.
Now, if you remember, the formula of power delivered was F dot V vector, isn't it? Yes.
Yes, yes.
So that means what? If I take, as you saw that this, as we know that this magnetic force, force experienced, you should say force experienced in external magnetic field force experienced by charged particle in external magnetic field is always perpendicular to velocity, isn't it? Right now we found out that this force is always perpendicular to the velocity, isn't it?
Yeah.
This implies that F dot V vector is always 0. So can we say that the power by the magnetic field, power delivered by the magnetic field on the charged particle is always 0? Yes or no?
Yes.
So what is
Yeah,
the
yeah,
power delivered is also how much? 0. So basically we can, tell me.
yeah, yeah, actually, yeah. Makes sense.
So this implies one
Because I,
biggest important point, that the work done by this magnetic field is always going to be equal to 0. So three conclusions. First, force is observer dependent. Second thing, force is perpendicular to velocity and magnetic field. So if this force is perpendicular to magnetic field and velocity, that means power delivered by magnetic field is 0. Uh, That means the work done by this magnetic field is also how much? 0. Are you able to get me or not?
zero. Yes.
So question arises, where does this force is used? So simple. This basically, if this work done by the magnetic field is 0, that means that, does my magnetic field is a conservative force? That's
Yes.
that's a question for you to reply. That's, I'm giving you as a question, not answer. Got it or not? So question is, we'll talk about this. Remind me tomorrow. Does magnetic field is conservative field or non-conservative
Yes.
field? If it is conservative, tell me why. If it is non-conservative, then tell me why. Because if it is conservative, then Ampere-Circuital law should not be should not be that much valid. Got it or not? So you have to tell me how to consider it.
Wait, what
We'll
exactly that?
abolish this statement. Just we'll talk about that. First, you saw in see in the internet, see in the NCRT book that whether the magnetic field is conservative or not. Got it or not? That's your task to study.
Okay.
Okay. Remember our definition of conservative fields? We have 5 points which we described in work or energy for conservative field, isn't it?
Yeah.
Okay, now next point, if this work done by the magnetic field is 0, so basically we write work done as integral F dot das. So that means displacement vector is itself how much? 0. Are you able to get me or not?
Yes.
So basically this means one of the biggest important point, that what this force is doing. That means the question arises, then what this magnetic force is really doing, isn't it? See,
Yes.
basically all the work is 0, work done is 0, power is 0. So why this magnetic force is present? So basically it has a very good answer. Remember that it's only helping, this magnetic force, it is only helping to change the direction of velocity of particle but not the but not the magnitude of velocity of particle.
Could you explain that? I didn't
Yes, yes.
understand it.
I'll explain. Definitely, I'll explain.
Oh,
Okay, you see one thing. Is this force is doing any work?
no,
Is this force is generating any acceleration?
no.
Yes. The answer is yes. The force generates the acceleration. Listen, listen, listen. The force generates the acceleration. This force is very, very good. Force is doing something, but that force is not doing a work because the net displacement ultimately becomes how much? Zero. Means whatever what is happening, you can imagine like this way that let's suppose I have a charge particle.
Okay.
Okay. So let's suppose I took one charge particle and I took one field. I took one magnetic field. This cross sign represents the direction of magnetic
Physical
field.
thing.
Okay.
Okay.
Let me draw it perfectly. So this cross sign represents the direction of magnetic field. Like some magnetic fields are present in this region. Are you able to get me or not? Got it.
Okay.
And in this magnetic field region, what I took a charge particle and I provided it some velocity. Right or not? I provided it some velocity.
What is the range on that?
What is that? That is a charge particle.
Range.
That is a charge particle, and I provided some velocity to the charge particle. Ultimately, what I found out that as we know, the force applied will be perpendicular to the velocity and magnetic field both, isn't it? So, does the charge
Ah,
particle will experience the force along this direction or not? Tell me, sir.
yes, force is perpendicular to velocity. That's
Yes. So, this is the direction of what? Force towards the center.
force.
Now, if force acts perpendicular to the velocity, what does it actually does? Is it going to change the magnitude of velocity? Tell me. If force
No.
acts perpendicular to velocity, then what it will do? Nothing. If force is along some velocity direction, then there will be some acceleration along this, and then the velocity magnitude will change. Otherwise, this force is working like a centripetal force or not.
Force acts in equilibrium. Yeah, centrifugal.
Yes. So it works like which kind of a force?
It is generating
Yes.
force.
So basically, the force which is generated by magnetic field is almost a centripetal force, which is only changing the direction of the particle at every moment of time. It's always perpendicular, right or not? So what it will do? It will
That's
always,
what centrifugal. So like that's what centrifugal force does.
yes, it always changes the direction of particle at every moment of time, right or not?
Yes.
Is this clear?
Yeah. It changes the direction of the particle.
Yes. Direction of what? Velocity of the particle.
Direction of velocity of particle.
So does is it changing the magnitude of velocity? No, centripetal does not
No.
changes the magnitude. So if it is acting perpendicular, it is a centripetal force. Second point is it only changes the direction of charged particle. Third point, uh, the magnitude of velocity does not changes. The magnitude of speed basically. The magnitude of velocity means speed, isn't it?
Yeah.
Speed
Yeah.
of charged particle does not change.
Yeah.
Now, as the speed of the charged particle does not change, the kinetic energy of charged particle also does not change.
It's constant.
Yes. Are you able to get me or not? So remember,
Yeah,
yeah, so if a charged particle with some velocity is thrown in a magnetic field, perpendicular magnetic field, we feel that the body does not experiences any kind of change in speed. That means that kinetic energy of the particle does not changes. Means the clear idea is magnetic force cannot change the speed and the kinetic energy of the particle. Are you able to get me or not?
yes,
But it can change the velocity because direction changes. Are you able to get me or not?
yeah, yeah.
Yes, it can change the momentum of the particle because direction changes. So what does it changes? It changes
The direction.
it changes velocity because not in terms of
That.
no, it changes velocity in terms of direction, not in terms of magnitude. Are you able to get me or not?
Yes.
Okay. If it changes velocity, then it changes also changes the momentum.
That is actually. Yes. That is actually.
Is this clear or not?
Yeah.
Got it? And this is why this force is called as Lorentz force. What it is called as?
Lorentz
Lorentz
force.
force.
Has like okay.
Okay, so we got two to three important points. First thing is Lorentz force. Second thing is to talk about, let's suppose if I'm talking about any kind of charged particle thrown in the magnetic field, then it experiences any kind of a force which is always perpendicular to the velocity of the particle, which makes the if the magnetic field is big enough, then the charged particle starts to rotate in a circular way every time with some force equal to bqv, and here this force will be exactly equal to bqv or not? Tell me yes or no. Yes, yes. And as this force is exactly equal to, you can say me, basically it is rotating in some kind of a radius of r or not.
Yes.
Yes. So if I consider any charged particle and if I am talking about non-inertial frame, then the body is experiencing a centrifugal force outside, which is mvs square by r or not. If the mass is considerable enough, and if this is a horizontal plane, which kind of a plane it is? Right or not? Not a vertical plane, such that mg will be considered. If it is a horizontal plane, then it must be my mv square by r must be equal to bqv or not. So v got
Yes.
cancelled, and I got to know that what can be this radius of the path. Therefore, radius of circular path, if it completes the full circle, is equal to how much? mv by qv. Are you able to get me up?
Yes.
Clear?
That is not.
Okay. So write this, then I'll move ahead.
Okay. Yeah.
Okay, so the point is very simple. Now let us think, as I have, this is the meaning of Lorentz force. Now let's suppose if this charge particle, if any kind of a charge particle, okay, let's suppose this is my charge particle and it is thrown in some field which has
What's
both electric and magnetic field. Okay, so this is, let's suppose the charge particle is thrown, charge particle of charge q is thrown in an electric field, and here magnetic field is also present. Okay, and it has originally some direction of velocity along this. Then the force experienced by this charge particle, or we say that force experienced by charged particle in the electromagnetic field is given by F is equal to QV vector plus QV cross B. Are you able to get me or not? So basically I can take this force, this is the total force, and if I take charge common, it is E plus V cross V vector, and that is my force which is experienced by any charge particle in both combined electric field and magnetic field. Are you able to get me or not?
Yes.
Got it?
Yeah.
So now we will see what we are going to do. We will let, as we know that electric field does something, magnetic field does something on a charged particle, and a combined electric and magnetic field will also do something on a charged particle, isn't it? So what we will do,
Yes.
we'll start taking one case. We'll first throw the charged particle in only a magnetic field, then we'll throw in electric field. Word on. And
Okay.
then see, basically electric field throwing we have done, isn't it? When it was thrown, it was deflected, isn't it?
Yeah.
Yes. Did we have done,
Yeah.
done
Yeah.
now?
Yeah. We did.
Okay, so if it is thrown in electric field, if it is thrown in magnetic field, what actually happens to charged particle? We'll talk about that. Go ahead or not?
Yeah.
Okay, so let me talk. Let me first take first case. Charge thrown. Let us do the electric field also. Let charge thrown in the uniform electric field. Got it?
Okay.
So let's suppose I have some charge, I have some field. Okay,
Okay.
let's draw this. This is the direction of electric field. Got it or not? And a charged particle is brought in that. Got it? This is my charged particle. And we have some different cases. First case is, let us talk about that. First case, charge is released from rest. If it is released from rest, means initially its velocity was how much? Zero.
Zero.
Yes. So initially if its velocity is zero, but if this charged particle has charge q and mass m, this charged particle will feel the force along the direction of electric field or not? Always.
Hmm?
Yes.
Yes.
So that
Yeah.
force will be exactly equal to Q into electric field. And ultimately, the charged particle will experience an acceleration. What it will feel? Acceleration, and that will be
Accelerate.
exactly equal to QV by how much? M. Are you able to get me or not?
Yes. Yeah. Yeah. Got it.
Clear?
Yeah.
So, charge, point is, if charge is released from rest, you will feel that. Hello, मैं क्लास ले रहा हूँ. क्लास ले, मैं ऑनलाइन क्लास ले रहा हूँ. क्लास ले रहा हूँ. Okay. So, this charge particle feels the force along the electric field. Right or not?
Yes.
And that force is going to drive the charged particle along the electric field, which makes it move along the electric field. Got it or not, guys? Got it or not? Celestine, is this
Yes.
clear?
Yeah. 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 Got it.
Second case. Second case is same charge, but this initial velocity is parallel to the, means it is released charge with some initial velocity parallel to the magnetic field. Sorry, electric field. What I'm saying.
Yeah,
So once again, it will feel same acceleration. Acceleration will be same. Just final velocity will follow v is equal to u plus a vector t vector. Are you able to get me or not?
yes,
Yes, it starts to move along the direction of electric field only with a faster rate. Are you able to get me?
yes,
Now, third case, what if the charge starts with or charge or you can say the initial velocity of charge.
Wait, can you repeat that second case again? What will happen?
Simple. Second case, if initial velocity is there, so this acceleration will only work. The final velocity will be v is equal to u plus at after time t. Got it or not? Nothing changes. Okay. Just the initial velocity gets added with the extra velocity which is produced by acceleration in time t. Are you able to get me or not? Clear?
Yes,
So third point is if this initial velocity is perpendicular to the electric field, then what happens? That is a big question. Tell me, what will happen if the charged particle experiences a let us yes, if it experiences such a velocity which is perpendicular to the electric field, then
wow, okay.
what happens? Let us discuss this in detail. It cannot be completed within one page. Two cases you understood. Let us discuss this in a great detail. If a charged particle, third case we are studying, if initial velocity of charged particle is perpendicular to the electric field, then tell me what will happen. Means, let's suppose this is a charged particle. Okay,
Yes,
it has a mass charge q, mass m. Okay, and its
yes,
initial velocity was along this direction, or let us see, its initial velocity was along this direction, along x
yes,
axis. Let us draw one x axis and y axis, then it will be very good to understand. This is x and that is y. Okay,
okay,
so its initial velocity was along x axis. Then I suddenly switched on an electric field present along the direction of y-axis, perpendicular to the direction of initial velocity. Got it?
yes.
Then what will happen to the charged particle? That's what you have to find. Which path it will follow, that's what you have to tell.
Uh,
Think and do it. It's easy. Tell me what will happen. See, so to understand that, first write the equations, Balak. See, there are two paths, horizontal and vertical, isn't it? You only tell me. Whenever you get these questions, divide, na, divide. Horizontal path, vertical path. Right or not?
Yeah.
This is basically horizontal. I have some initial velocity, ux, that is given as u. If electric field is there, then the force is along the vertical direction only or not? Tell me yes or no.
Yeah.
There is no force along the horizontal direction. So acceleration along horizontal is how much? Zero.
Zero.
Let's suppose the particle travels displacement along horizontal and that is equal to some distance x. Are you able to get me or not?
Yeah.
And that is traveled in some time of traveling is t. If you want, see, there is a playlist I'll share you today of projectile which is going on. Okay, on my YouTube channel, you watch that projectile part, then you will be able to understand about this thing in a very very good way. Got it or not?
Yeah.
Okay, so I'll share you that link by today night only. It is going on, so you can see one topic and you can complete the DVPs also. Is that clear?
Yeah.
So look over here. If you have horizontal path, initial velocity is u, acceleration along horizontal is zero, displacement is, let's say, some x coordinate after time t, and time of traveling is t. Are you able to get me or not?
Yeah.
So basically, if you look over the vertical path, there is no initial velocity along vertical, isn't it? Uy is how much?
No.
Zero.
Ui is zero.
Yes. But as acceleration is there and if the charge is positive, the charge will feel some force. That means there is an acceleration along y direction, which is exactly equal to qv by m or not. Tell me yes or no.
Yes.
Let's suppose after time t, displacement is y and time of traveling is y basically. So what will happen? Basically, this force which acts
Time
perpendicular,
of traveling is y.
sorry, t. Basically, the point is very, very simple. You know that whenever the force acts perpendicular to velocity, it starts to change the direction of velocity, isn't it? So particle will, instead of going straight, what will you will find that the particle is going in a curvical way, isn't it? So there
What
is
way?
curvical way,
Vertical way.
and
Achha.
we will
Like
find that what
that
is
is
this
very
curvical path, right or not?
that is very well deviated also.
Yeah, deviation is there. Question arises whether this curvical path is circular, what kind of that we do not know. Na? We have to calculate that. But we know that it is going to feel a curve. It will feel a deviation. Let's suppose the deviation created along this path is theta from the horizontal. How much is that? Theta. So basically, we can find now how much is this deviation or what is this basically. Look over. Let's suppose if a particle is over here, then does this particle have some y coordinate and some x coordinate in time t or not?
Yeah.
Yes,
Yes.
this particle has some x comma y. What is this? X. X is this length
Yes.
and y is this length. Are you able to get me or not?
Yes.
So what is this x? Simple. I can write the displacement equation. Can I apply in both the equations? S is equal to ut plus half at square.
Yeah.
So here acceleration is zero. So x is simply equal to ut because acceleration is zero over here. Are you able to get me or not? If I apply in this equation, downward vertical equation, so here I got x is equal to ut. If if I apply y, initial velocity is 0, so y is directly equal to half acceleration along y into t square or not.
Yes.
What is acceleration along y? Half qv by m
QE by
into t square. So you got your displacement along x, you got your displacement along y. Now can you replace t is equal to x by u in this equation or not? So what it
yes.
is? Y is equal to
So
half
that's half value.
qv by m. Yes, that is a trajectory equation, x square by u square. So basically this is written as, in simple form, y is equal to qv by twice m u square x square, and this is the equation of parabola or not?
Yes. Useful.
Correct?
Yeah.
So if this is the equation of parabola, that means this trajectory, this curvical path is nothing but a
Parabolic power.
parabolic path, and the angle theta deviation is nothing but, can I apply tan theta to get the deviation? Tan
Yes.
theta is equal to y by x, y is qv by m t square, so half qv by m t square, and x is u into t, tt got cancelled, so this implies tan theta is equal to qvt by twice m, and that is the calculation, that is the method to calculate the deviation. This is the calculation for angle of deviation. Are you able to get me or not?
Yes.
Is this clear?
Yes.
So this is what happens if the particle has some initial velocity perpendicular to the force, or if you say electric field is perpendicular to the initial velocity of the particle when the particle is thrown inside a electric field. Are you able to get me or not? Clear?
Yes.
Now, if the initial velocity is making some angle theta with the electric field, then both the trajectories will feel the electric force. Are you able to get me or not? And that is the calculation best for you. Okay. So first is released from rest. Second one is parallel to the electric field. Third, perpendicular to the electric field, and fourth, some angle theta to the electric field. And both those electric fields will generate some force. You can write those equations and see what will happen to the part. But now let us imagine, what if the same particle is thrown in a magnetic field? Electromagnetic not, in a just a magnetic field. Charge,
Uniform magnetic.
yes. Hold on. So once again, let us discuss first case, when charge is released from this. Then tell me what will happen.
Then this
Tell me. Think and tell me fast. One minute.
So what do we exactly have to find? Like
What happens if the charge is released in a uniform magnetic field at rest? Tell me the condition. What will happen? Yes, initial velocity is zero. Then what will happen? That's what I'm asking. That's so. Array, you said the answer by yourself only. If initial velocity is zero, then nothing happens because you know that the force on the magnetic field is dependent on velocity. If velocity is itself zero, what will happen to the force? Zero.
Yeah.
Got it?
So it is depending on
So here it is not about electric field. Here it is about the velocity and magnetic field. So as velocity is zero, force due to magnetic field is zero. Remember that. So if it is at rest, the particle remains at rest only.
it is released from rest.
Yes. Word or not?
Yes.
Second case, charge initial velocity. You can write directly. Initial velocity is parallel to the magnetic field. Then what will happen? Tell me.
Wait. Yes. Parallel.
Yes.
That means F is zero in this case.
Force is how much?
Zero.
Means
So the
mag-
angle between the magnetic field and
yes.
the
So force
velocity
is
is
zero if theta is 0 degree or 180 degree, isn't it? So does this apply that axle?
when you parallel it, so it is zero.
Yeah. So does this imply?
That happens between these.
Hmm. So if it
Yeah,
is
just one minute.
if it is parallel, then the angle made by the velocity and magnetic field is always 0 or 180. Right or not? 180 in the sense of anti-parallel, but I'm considering it.
That
Yeah.
happens.
So basically, magnetic force is 0. This implies acceleration is how much? 0, isn't it? So if
Yeah. So
acceleration
this
is 0, then what happens to the initial velocity? That means that the particle,
that the velocity is constant actually.
yes, the particle
Constant velocity.
moves with constant velocity, isn't it?
That's right.
Correct.
Yes.
So that means the path is a path of particle.
It's in a straight line.
It is a straight line.
Straight line. Yeah.
Correct.
Yes.
Or you can say undeviated path, as
Like it
it is.
will be parallel to the x-axis or something like that.
Anything. If it is going in anywhere direction, it will be along that same path only. Word or not?
Yeah, it will be going in x-axis and it will be parallel.
So, but then, what if our initial velocity is perpendicular to the magnetic field? The third case, if initial velocity,
Then it goes to QV,
thing is perpendicular to the magnetic field. Yes, force is correct. But then, what is the meaning of that? Tell me about acceleration and all those factors. Okay.
Where it is this starts to
Mm-hmm.
no 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 wait wait. A will be QVB by M.
Uh-huh.
A will be QVB by M.
A will be QV by M.
Yeah, because M.
Thing. Hmm, draw the trajectory, then you can understand.
Wait, so the initial velocity is about this much.
Uh-huh.
It is to wait a minute.
Think what will happen.
Yeah, yeah.
1 minute, just 1 minute, then I'll explain. Try it, then I'll explain. Okay.
Yeah. 1 minute. Yeah. 1 minute. Okay, I got the equation of the trajectory.
Hmm.
I got the equation of the trajectory.
Why
Now
it is
I'm just
required? Trajectory is
huh?
okay. Let us do it.
Okay.
You got the equation of trajectory. Okay. What will be that?
That is equal to half of q v by l v square into l c square.
Nice to think. Let us start this then. So you got the equation of trajectory, isn't it? Means, let's suppose a charged particle, okay, with
Acha.
some velocity. This is my charged particle, isn't it?
Okay.
I just send them. Means, let's suppose this is charged particle Q. Let me draw it big. Okay. This is charged particle Q having mass m. It is thrown with some velocity in the perpendicular magnetic field, isn't it?
Okay, good.
Correct? Then what happens? Let us see that. What happens to this charged particle is that this charged particle attains or it travels in a circular path. Which kind of a path?
Circular.
Yes.
Okay, okay.
What happens to this path of the particle? That it travels, starts to travel in a circular path. Word or not? Is that clear?
Okay.
Like it will feel like that this charged particle is rotating in this circular path with some radius. Are you able to get me or not?
Okay.
Okay.
Oh, like that.
Yes. So that's my point. Whenever you have this velocity of the charged particle or something like that, then you will feel that this charged particle is always rotating. Got it?
Yeah.
Now, and as this path of the particle is circular, basically I'll draw a perfect, means I'll erase these big things. Okay, I'll draw it in a simple way. Okay, so let's suppose if I consider a charged particle in reality inside a magnetic field which has some mass, charge q, and mass how much, m, and it has some velocity, then you will feel that the charged particle is rotating in a circular path with some fixed radius. What kind of radius it will be?
That's
Fixed radius. Are you able to get me or not?
yeah, yeah, I get it.
Is this clear?
It's clear.
Yeah. So
Yeah.
radius of the charged particle will find out that it is fixed. That means that, as we know, that the charged particle experiences that kind of a force which is towards the center. So basically, here the trajectory is already determined. Are you able to get me or not? So the motion of the particle is already fixed. It is circular motion. Word or not?
Okay.
Here, when I was considering electric field, then it was a parabolic motion, like a projectile. But this is not a projectile. This does not create another velocity. Here in electric field, what used to happen? This electric field used to generate a velocity. Are you able to get me or not? With the help of a force. Not it.
Generate velocity,
Yes.
but
Yeah.
but it is written that what will are vy is equal to
Are initial velocity is zero, na? Final velocity will be zero.
no, no.
It will not be zero, na? So it's generate
Yeah.
the velocity. But here, as this force, because see, what happens over here is,
It is not altered with the magnitude of velocity.
because the point is, not every time this force is perpendicular to initial velocity. Over here, force is upward and initial velocity is like this way. This is the direction of velocity. Force is upwards and velocity is like this way. So what is happening? This force is able to change the magnitude of velocity plus direction also. Are you able to get me or not?
Okay.
Okay, so but this force, what happens with this force? That this force is idiot force. That whenever, what happens? That whenever the charge particle is changing its velocity, this force guy is very bad. He is not able to think properly. What he does is simply he changes, okay, he changes its own direction of force also. Are you able to get me or not?
Acha. Okay, like that.
Yes. So this is the most important point of the magnetic force, that this is a self-orienting force, you can say. Are you able to get me or not?
Self adjusting force. Yeah,
Yeah,
that's okay.
basically. So always this force is perpendicular. Here, opposite thing used to happen. This force is not a self-orienting force. It is fixed in one direction. Are you able to get me or not?
Yes.
So this is why this force, the force by the magnetic field, does not changes the magnitude of velocity.
Yeah.
The magnitude of velocity, and this is why this trajectory is a circular trajectory, not a parabolic trajectory. Is this clear?
Yes.
So basically here, if it is a circular trajectory, the trajectory equation is simple: x square plus y square is equal to r square, which you r square you find out using the method of force and all. Go it or not?
Yeah.
So second point, as this is circular trajectory, the velocity, speed of the particle remains constant. Okay,
Yes. Yeah.
and right now we calculated the radius of this path. Radius is simply, if calculated right now, it is equal to mb by qb, isn't it?
Hmm.
So the radius of the path is, what is that? Simple, mb by, I'm writing it
MV
as,
by QV.
yeah. Are you able to get me? But what
Yes.
is mb? Mb is momentum of the particle. So momentum by charge into magnetic field. Are you able to get me? What is momentum? So momentum, I'll write the whole bunch of equation. Remember that radius is equal to mb by qb. Need 2013 momentum by qb question. Need 2014 kinetic energy question. So momentum is twice mass into kinetic energy of the particle. Right or not?
Yeah.
Divided by qb. So need 2016 potential of the particle root under twice m q into capital V, where capital V means what? Potential, because kinetic energy also then is generated by the potential of the particle or not, divided by q. So these are four formulas of radius, right or not, which you need to always remember.
Oh my God. Okay.
Got it? Where capital V means potential,
Potential. Is it potential or potential difference?
potential difference, through which charge is moved. Are you able to get me or not?
So many formulas. Okay.
Mm-hmm.
So many formulas. Okay.
Yes, so many formulas, but each of have a very great meaning. Are you able to get me or not? So let us write these terms. P is our momentum. K is the kinetic energy. In many books, you'll see V as potential difference or accelerating voltage. Are you able to get me or not? So these are all
Yeah.
our terms which are helpful, or which are the reasons which the charge starts to rotate. Are you able to get me or not?
Yes.
Yes, so this implies that now question arises that we can find even the time period in which it will complete the whole circle or not.
Okay.
So this is called as time period denoted as capital T of charge, or time period of periodic motion you should write. Word on that. So that is how much is my time period? Simple. If you see in one revolution it completes one full circumference or not.
Yes.
So we are finding the time period of one periodic motion. Are you able to get me or not?
Yeah.
Okay, so if it is one periodic motion, then simple time period is 2 pi r by the velocity of the charged particle, isn't it? That is how much?
Yes.
2 pi r. Radius I can write v. Radius is mv by qb, isn't it?
Yes.
So this is equal to 2 pi m by qb. Are you able to get me or not?
Yes.
If I know my time period, I know my angular frequency also. Yes or no?
Like that. No.
It is denoted as omega.
No.
Okay, so omega is called as 2 pi by t. Right or not? So if I
Yes.
put 2 pi by t, it will become just qb by m. Are you able to get me or not?
Yes.
And last part, that is frequency of the, how much times it will oscillate within one periodic motion. Are you able to get me or not? Frequency f.
Yes.
Got it?
Here it is. Yeah.
Ah, qb by 2 pi. Correct. So frequency is 1 by time period, which is qb by 2 pi m. Are you able to get me or not?
Yes.
So you see all these things, that this these all things are independent of velocity of particle,
Yeah. Absolutely.
not velocity, sorry, independent of speed of particle.
Why did you just say speed like that?
Because if it is independent of speed of the particle, velocity means direction is also changing or not. So if it is independent, what is there? Basically, we can see that it only depends on the mass, amount of charge, or the magnitude of charge and the magnetic field. Right or not? It is not dependent
Yeah.
on the speed of the particle. Are you able to get me or not?
Yeah.
Got it. So what you are going to observe, let's suppose if case one is there, if I took the velocity or speed of the charged particle in the order as in order as like v1 is less than v2 is less than v3, means at different time t1 instant I have different speed of the charged particle. Right or not? And that charged
Okay.
particle was thrown in a magnetic field like this way. Are you able to get me or not?
Okay.
So what you are going to basically observe is a very nice phenomena now, that these charged particles, when I throw them inside this magnetic field, okay, so let's suppose if this is the path of one charged particle, got it? So if it is a small, look over here, does the radius of the charged particle is dependent upon the velocity of the charged particle or not? Yes. If
Yeah.
velocity is more,
Right.
radius is more. So this inner radius will be of what? Velocity v1 charged particle. If this charged particle is projected over here, what will happen? You will see that if this is my charged particle of mass m and I'm projecting over here, right or not? With different
Okay.
velocity. If I increase the velocity, the same shape, same size will suddenly increase. This radius of the path will suddenly increase, right or not? Isn't it?
When you do what?
Radius of the path will increase. Are you able to get me or not? Because the velocity has been increased.
अच्छा suddenly हाँ.
Ah. Suddenly, if I increase much more, what will happen? Much more velocity, much more radius will increase. Are you able to get me or not?
Is that a constant principle?
Yeah. So basically, you will observe that this the smallest circular radius is for R1. I'm considering it is MV1 by QB. Are you able to get me or not?
Yes.
When I consider the little bit farther one, which is R2, so R2 is equal to MV2 by QB, and R3 is equal to MV3 by QB. And as V1 is more than V2 is V1 is less than V2 and V3, that means R1 is less than R2 is less than R. But in all these cases, the mass and charge and the magnetic field is same or not? Tell me yes or no.
Yeah, 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 it is.
So, what is same over here? That in both of the cases, in all this path, the time period of revolution in all the paths are same. Angular frequency in all these revolutions are same. Total frequency is also what? Same in each path. Are you able to get me or not?
Yes.
So this is the most interesting result of the Lorentz force. Are you able to get me? That
Yes.
although the velocity increased, the radius was increased, but the time in first path, the time taken to revolve in second path, the time taken to revolve in third path, both are all same. Are you able to get me or not?
Yes.
Is this clear?
Yeah.
And this is what happens when the particle enters with some velocity perpendicular to the magnetic field. Are you able to get me or not?
Yes.
So tomorrow we will start with that initial velocity which is inclined at some angle theta to the magnetic field. Fourth case, which we didn't discussed in our electric field. Are you able to get me or not? And then we can
Yeah.
got it or not.
Yes.
Any kind of doubt till now?